But prime factorization is what lesson 65 was about. That's really just a big word that doesn't mean you do anything fancy. A lot of times these big long words are just extensions of simple words that you probably know.
To try and make them sound small.
Well, I don't think that we have a purpose like that. But prime factorization means write the number as a product of primes. So maybe you should write down that definition. Because some of you, when you read that and you think it doesn't look exactly like what I saw on the Delta Math or the homework, then you automatically freeze up and you're like, I don't know what to do. Okay, that's several of you. Okay, so let's work through that as a product of primes. Said another way, we're going to write these numbers as simple values multiplied. Simple or prime values. So, what's the definition of prime? What's the definition of prime?
It's something that can be multiplied by other numbers.
All right. All right. We got to fix your vocabulary right away. Prime means it only has one factor. Itself and one. Okay? So you got to think it can't be multiplied by something. No, any number can be multiplied by any other number. You've got to go the opposite direction. We're not multiplying. We're thinking of factors that multiply to get this value. So 72 is or is not prime? It's definitely not prime. Okay, here's where there's a little freedom. Some of you have too much of that right now. Here's a little freedom. You can start with any two numbers that multiply to get 72. Any two whole numbers. Okay? So 6 and 12 are what I heard at least one person say. We could do that, or we could start with 36 and 2. It would not matter because the end goal is the same. We want to break every factor down as much as possible. Okay? So we'll do 6 and 12 here. Now you'll notice I can keep going. So 6 can be broken down. 3 and 2. And we're going to stop, at least for that branch. Because 2 and 3 are both prime. We're going to break 12 down. 3 and 4. If you chose 6 and 2, that's okay as well. Either way, you're going to notice that the 3 is done, but the 4 is not. So that can be broken down further into 2 and 2. Now, the way we write our answer, once we get to this stopping point, let me back up a second. Why is this the stopping point?
They're all prime.
All the fruit at the bottom of the branch is prime. So that's what we're going to rewrite 72 as. Okay? 2 times 2 times 2 times 3 times 3. Okay? That is the prime factorization of 72. Or said another way, that is 72 written as a product, multiply, of prime numbers. Okay? Is there one other way we could write that? Maybe using another operation?
Yes.
Using exponents. Since 2 appears 3 times, we could write this as 2 to the third power, and then 3 appears twice, times 3 to the second power.
Are you going to do Quizlet today?
No.
I don't know what it's called.
We never do Quizlet. I don't do Quizlet. Okay, so what is 2 to the third, really? Well, that's 2 times 2 times 2. 8, for anybody thinking that way. And then 3 times 3, that's 9. What's 8 times 9? 72. Okay, so we can check ourselves here, but this is what I'm looking for. Liam, 1 minute after class, please. Letter B. And maybe we'll have done one of the ones from the practice set, but let's take a look at 108. Okay, 108. 108 is even. If you don't know that 9 and 12 make 108, just start with 2 and something. Any even number can be started with a 2. So we can do 2 and what to get 108? 54. 54 is still even. Why not stay with that theme of 2 and something else? 2 and what make 54?
Wait.
We are multiplying here. I did see one or two where people were just scribbling and they wrote things that add up. That is not what we're talking about here because factors have to do with multiplication. So 2 and
6.
27.
27. Question, Liam?
Oh.
You're going to tell me the answer to that. Well, Liam, how do you want to split 27 up?
9 and 3.
9 and 3. You notice I'm not doing anything with the 2's. Why not?
Because they're already prime.
They're already prime. I already finished that part. And then 9, 3, and 3. And what you're going to notice is 108 looks really similar to 72 by the time I rewrite it in primes. So I've got 2 2's and how many 3's?
3.
Got 3 of them. So what we'll do, we're going to compare these. 2 squared, 3 to the 3rd power. But I'm not expecting you to write this yet. Okay?
Oh.
I'm not saying don't write it down. You should write it down because it's coming. But now if we zoom back out for just a second and look at 72, that was 22233. And 108 is 22333. What might we be asked to do in the future? Well, we might actually learn that we can use prime factorization to reduce something like 72 over 108 if that was a fraction. Now, looking at it this way, it's a little bit more difficult. Not for everybody. That's a subjective question. Some people look at that and think, oh, that's easy. But the strategy here is based on, well, let's write the prime factors. Let's rewrite 72 as 2, 2, 2, 3, and 3. Let's rewrite 108 as 2, 2, 3, 3, and 3. And then have we learned something we can do when you have the factors listed like this on top and bottom? Cancel them out. They can cancel using what operation? When I put this slash through it, what am I actually doing? How am I getting 1 with a 2 on top and a 2 on bottom? What am I doing? Not multiplying. They're fractions. Yes. Yes. So think about this. I could expand this out and say this is like 2 over 2 times 2 over 2 times 2 over 3 times 3 over 3 times... Oh, they're... Now that would be more work. You might think that's redundant. Redundant means...
Useless.
Unnecessary. It doesn't mean useless, but it does mean unnecessary. Y'all don't use redundant. You know what y'all use?
Unnecessary.
Another word that starts
Well,
with R.
yes.
Unnecessary.
No.
Too much work.
Most of y'all just say extra.
Okay.
All right. But here's the thing. If you understand it and it helps you, it's not extra. It's helpful. So let's look at how this is helpful. As Macy's pointing out, we can cancel these out and they create a 1 and a 1 and this one and this one. So what is 72 over 108 as a reduced fraction? The only thing that didn't get reduced. Okay, so what just happened? We found the prime factorization of 72 and 108, and then hypothetically we said, well, what if that was a fraction, 72 over 108? It reduces to 2/3, and I can use the prime factorization to do that faster than thinking about, okay, well, what's the GCF of 72 and 108? The silence has proven my point.
What?
The silence proved my point, that question was harder to answer.
Can you repeat the question again?
What's the GCF of 72 and 108? Prove it. My point is proven.
No, you say it said 24.
It's 36. Now, can anybody find the GCF in our work?
No. Yeah.
2, 2.
Where is it, Leah?
I don't know.
You said yeah.
It's the 2.
No, it's not.
Because it's a 2, 2.
All right, now look. What did we cancel? Look, guys, look. What did we cancel?
The 2,
2, 2, 3, 3. What's 2 times 2?
4
Times 3
plus
times 3.
5.
36.
Keep up with that. We're moving quickly. 2 times 2 is 4, times 3 is 12, times 3 is 36. There's the GCF. That is what canceled. That is how this fraction reduction thing works most efficiently. All right. So I've combined a whole bunch of things into one problem here But that's really why I love math. So you're welcome. Letter C, it was 216. So if we continue this process of finding the prime factorization, that's not one from your multiplication facts from the third grade. Okay? And so those are just the basics, right? The ones that what do you call them? Times tables? Multiplication facts? Whatever you want to call them.
Wait, times table.
Yeah, and it's super helpful, and I would say necessary. But,
7 and 8.
27 and 8
27.
is an interesting pair there. I'm gonna pretend like I don't know that one. 'Cause I didn't think of that one. I have another one in mind, but I'm gonna skip that too because here's the thing. I've been doing this for.
7.
Hang on now. How old are you? Like 11?
11, 12.
I'm turning 12 soon.
I've been doing this for more than twice your lifetime, so I have a lot more practice. So when you wonder how does he do that in his head, because I've been doing it for a long time. So I'm not expecting you to do that, huh? 108 and 2, I like it. Now, here's why I like it. Anybody in the 6th grade should be able to see that that's even and know. Remind me not to go to the movies with Autumn. 2 and 108. Because everybody would stare at all the crinkles. That's what my mom did.
You'll be like,
That's why I'm like opening their bag of chips that they snuck into the movie theater because they didn't want to pay for the really expensive candy.
Parents have a whole entire bucket.
amen, brother.
So we're going to be thinking in the movie theater. I just put it in my bucket.
All right. I've gotten you off track. I'm sorry. All right. 2 and 108. Because, McKenna? Well, very good. I was just saying, why'd you choose 2 and 108 for 216? Because 216 is what kind of number? Even. All right, so I didn't even pick up on that, but McKenna has pointed out, we actually just did 108. So let's copy that over. So there's going to be a 2, and then the 108, if we bring it down from up here, 2 and 2. Let's see if I can squeeze all that on the same screen for you. And then 3, 3, and 3. Okay, so what do I get? I get 3 2s, 3 3s. Or I can write that as 2 to the third times 3 to the third. Okay, which points out a really cool cubic property. Points out a really cool cubic property. What's 2 times 3?
6.
So we could actually say, even though this wouldn't be prime, we could say that 216 is 6 to the third power. Do you see where I got the 6?
Mm-hmm. No.
2 times 3.
Because he did 2 times straight and he used it.
Right? We could even check it.
Check what?
6 to the third power. So nice. All right. So there's our prime factorization. Last problem. Here we go. Last problem is 625. All right. Can we start with 2 on this one? No, because it's odd. Okay. What can we start with? 5. Now, do you think it was coincidence that, I don't know, 3 or 4 months ago we did multiplication rules or facts? How do you know actually it's divisibility. How do you know when a number is divisible by 5?
It's always been 3 months.
It ends in 5 or 0. It ends in 5. That's for 3. That's for 3. So, that ends in 5. Check. So, 5 and something. 5 and something. And I'll help you out here. It's 125. 5's prime, so I'm done with that part of the branch. 125 still ends in 5, so still we should try 5. 25. And then we can go to this one. 5 and 5. Okay, so 625 is equal to, or what was that, Macy?
5 to the 4th power.
Yeah. Okay. So I will accept either one of these. They're both correct.
So,
5 times, no, the dot, right? You remember what the dot means?
multiply.
Yeah, it means multiply. I'm not going to write the X anymore as long as I can help it. Okay? Yes?
But what if someone forgets?
Do what? What if someone forgets? X? No. We'll see.
All the people who are arms in the bathroom.
Yeah, I know. Questions about... I don't, if to my knowledge, they haven't been caught doing pull-ups in the bathroom, so I think it should be okay. All right. Are there any questions about the warm-up problems? Are there any questions? So there were a couple questions that people needed help on the practice set from the book. So can you remind me what those were?
My mom helped me.
That's good. That's what's supposed to happen. I love it. So you said B.
What?
What questions did you need help on?
B and F. B-O-L, okay. B and F.
I think I needed help on.
All right. You guys might need to remind me what the problem was.
I think it was E I needed help on.
All right. So BFE. Is that the country? Is that what people say? Country.
Buffet.
Joe Biffy. Okay. So write the prime factorization of each composite number in problem A. So if you get to a word like composite and you're like, well, I don't know what prime, I know what prime is, but I don't know what composite, it's just the opposite. Okay, so aside from 1, every other number that isn't prime we say is composite. So fill in this blank for me. All blank numbers are composite, except for 2.
Prime. No.
All blank numbers. Even.
Got it.
Okay. Even. All right. So B says write the prime factorization of the composite numbers. So 20 and 21 and 22. So if you look at A, 19, 20, 21, 22, and 23, 19 is prime. 23 is prime. All of the others are therefore more Chromebook. Go ahead. Take what you need. 20, 21, and 22, however, are what kind of number?
They're
Not prime. What's it called?
composite.
Composite. All right, so that's why I listed them in part B.
Composite.
All right. So I'm going to start from the back. 22 is going to be really easy because it's even. I can do 2 and what?
11.
Can I stop?
No, yes. No, yes.
They're both prime. 21.
7 and 3.
Can I stop?
Yes.
4.
Yes, because 3 and 7 are prime.
4 and 5.
Can I stop?
No.
No, because 4 isn't done.
2.
2 and 2. Okay? E. 125 is a product of prime factors. We actually have already done that because we did 625. But we'll recap here. 125 ends in a 5, so you can divide by 5. 25 breaks down further into. So we got 5, 5, and 5. Or, okay. What's that called again? The little number up here?
Oh, third power.
Exponents. Exponents. All right. Problem F. Write the prime factorization of 10 and 100. Then look for a pattern to help you find the prime factorization of 1,000. Okay, so when we do these, 10 is pretty simple. Let me zoom in just a little bit here. 5 and 2, right? Okay. So 100. 50 and 2. And then 50. 5 and 10. And then 10. All right, 5 and 2. Now, wait. Because we want to actually have something to work on to see a pattern. So 10 is 2 times 5. 100 is 2 times 2 times 5 times 5. Stop. Don't blurt anything out. All I did was copy over what's at the bottom of my factor tree. So you should be able to see a pattern showing up here. So what do we hypothesize? That means guess. Based on what we see here for 1,000. Okay, so I want to see if anybody else thinks the same thing that McKenna said. You notice there's a 2 times 5. Now it's double 2 and double 5.
No.
Now it's triple and triple.
Yeah. What does that make? I see.
Zeros is how many 2s and 5.
Oh, okay. You could automatically look at the number of zeros. Well, let's think 2 times 2 times 2 is 8. 5 times 5 times 5, 125. 125 times 8.
1,000.
Is it? Just guess.
1,000.
Well, let's think. Let's do this intelligently. 125 times 8.
It's 1,000.
It is 1,000. Here's
I was
how.
right.
8 times 100 and 8 times 25. That's my 800.
That makes no sense.
That's my 200 for a total of.
I did that 1,025.
Very good. That's how I would do it in my head. All right, so that is correct. That's correct. What's the help? What's the benefit of being able to see a pattern like this? Well, then I could say, okay, well, what's the prime factorization of 10,000? And if you heard McKenna, I think you're going to figure it out. What is it? What'd you say, Liam?
2 to the 4th power. And 5 to the 4th power.
Times 5 to the 4th power. Okay? So that would be 16 times 625. Maybe we'll use a calculator. Just for the sake of time. Okay, so I'm not a cheater. 625 times 16. All right, fantastic. All right, so numbers. That's a trick, bless you, because we're not going to multiply them when they're mixed numbers. We're going to change it, okay? So the order of steps here, we're going to change both, if necessary, to improper fractions, okay? Then we're going to multiply. And then we can convert at the end as needed. So here's how that looks. I like that these are nice bite-sized, these lessons anyway. So suppose we had to do 2.5 times 3 3/4. I wish it were as simple as just saying 2 times 3 and then a half times 3/4, but it's not. You see, how do you read this? We say 2.5. So don't write this next part. What this means is 2 plus 1/2 times 3 plus 3/4. We haven't learned how to multiply those several things here. All right, so somebody have a question about what I wrote?
Yeah.
Number 1 says change both to improper fraction. Number 2, then multiply as normal. Number 3, convert at end. That's like the at symbol.
It's just saving a letter.
All right, so for now, we don't know how to do that. You'll actually learn how to do that.
Can we do the exam, please? Can I see the answer?
No, not yet. Let's just see if you got it right. So change both to an improper fraction. So 2.5 is an improper fraction. How do I do that?
You times 7 by the denominator, and then you add whatever the denominator.
Okay. Multiply the denominator, add the numerator.
Yeah.
Denominator doesn't change. Good.
Oh, we read.
3 times 4. Yes, you do write this one. This is the one I didn't want you to write.
Oh.
3 times 4 plus 3. We get 15/4. So what does multiply as normal look like? Top times the top, bottom times the bottom. I'm going to get 75 over 8. Now we're going to, so here's step 1. Here was step 2. And then step 3, convert as needed. Step 3, 75 over 8 is equal to 9 3/8. Is that not what you got? Okay. So here's why I said that's what it means. So you don't just multiply the 2 and the 3 in the fraction. You've got to do these 3 steps that I gave you at the beginning. Okay? You've got to convert it to an improper fraction. Then multiply. And then if you want to convert at the end, that would be the time to do it. Okay?
Stop.
Questions about that example? All right, so let me have you guys try another one based on that before we move on to lesson 67. Ooh, we might already have done 67. We did. So that gives us a little more time. We can slow down a little bit for 66.2. So let's do 1 and 7/8 times 4 and 2/5. So that's the one I want you to try.
Stop.
Pick up your pencil and put it down there. Okay, I want you to try 66.2. 1 times 8 plus 7, we're going to get 15 over 8 times 4 times 5 plus 2, 22/5. All right, so that's step 1. Rewrite as improper fractions. Step 2 is to multiply as normal. But I feel like I can go ahead and skip an entire lesson if I show you this one little adaptation here. This means 15 times 22 over 8 times 5, doesn't it? It does. It does. Okay? And I know some of you are just like, well, can't we just go ahead and multiply? I'd say yes, but wait. I want you to see something that's going to be really helpful. So, does the order of multiplication matter? No, it does not. Therefore, I could change the order any way I wanted. Now look at what happens. 15 times 22, I left that the same, but let's say I wrote it 5 times 8. Do you guys want to keep those beads, or would you like me to get rid of them? Please put them away. I don't want to see them again. What is 15 over 5? Does that reduce?
Yes.
What does it reduce to? I can cancel that out and just put 3 over 1. The same way that we did over here when we reduced parts of fractions that we're already going to multiply. We're actually allowed to do that here as well. 22 over 8. Can that reduce any? They're both even, so yes. 11 and 4. Now, why would that be helpful? Because it makes the numbers a whole lot smaller. There's nothing wrong with large numbers. Everybody seems to want that on their paycheck. But when you're doing the math mentally, smaller numbers are helpful because now you can make it easy to see 3 times 11, that's 33. 1 times 4 is 4 for my final answer of 8 and 1/4. 8 and 1/4 should be the correct answer. Now look, I showed you this in preparation for a future lesson that I'm probably going to skim over really quickly next week. But it doesn't mean I haven't taught it, because throughout the last 30 minutes or so, we've looked at how this applies to us. So, what happens though if you forget that? Can you still get the right answer if you do 15 times 22 and 8 times 5?
No. Yes.
If you do it correctly, yes. So 15 times 22, 330. 8 times 5, 40. What do you notice about both of these numbers? Look at the 0 on the end. And you get 33/4. 10 can go into them. 33/4. Did you see that in the way that we did the problem? There's so much beauty in mathematics if you stop and look for it, okay? All right, and then we get 8 and 1/4 from that. So, the 3 steps, if you haven't written them down, write them down right now. Okay. If I can get that to where you can see it. Change to an improper fraction, multiply as normal, reduce or convert at the end.
Do I need to highlight that?
If you want. I just want you to write it down. I'd be happy if you guys would write down the stuff that I spend the time to write down.
What is the top one?
Change both to an improper fraction. Okay. So, what does this have to do with lesson 67? Well, for anybody following along, and it's okay if you don't have your book out right now, I've given you enough information to go off of that. We actually already did lesson 67 when we did the warm-up. I'm going to show you how.
What does
Okay?
that mean? That is that like a sad smile?
That means we don't know how to do it yet. This is what people put on their paper.
Can
That is the bane of teachers' existence.
That looks like 100K.
That looks like 100,000.
All right.
It looks like
Sophia, question? Let me finish this and you can. All right, so have you got what you need? Yes, sir. Yeah.
Wait, no, I can't. Is that better called?
As you guys get older and you advance in your grades, assuming you're going to pass this class, you're going to find out that teachers don't tell you wrote this down. You're just supposed to know it, okay?
I can't see the second one.
You're still writing that down?
We're supposed to have it.
All right. I'm not trying to be rude. I'm trying to be real. My wife always tells her kids, before you say something, is it true? Is it kind? Is it helpful?
Nice?
It's helpful.
Ella.
And I'll be honest. I'm just honest. It's just true with me sometimes. All right. So change both to an improper fraction, multiply as normal, convert at the end. One way that you're going to figure that out is that if you try to do it without converting, you get the wrong answer over and over and over. You realize, there were 3 steps I'm supposed to do. Okay? All right. So lesson 67, if you're all ready for it.
No. Wait. Yeah,
Not mentally.
Yep. But physically.
Well,
Not physically yet.
lesson 67 is what we did with 72 and 108 using the prime factorization. Okay? So, pencils. Rosalie, you good? Okay, cool.
How much time do we have left until we leave? 5 minutes.
You have longer than everybody else, so don't worry about it.
Like 7 minutes.
All right, so we're going to reduce using, wait for it, the prime factorization, okay? So we're combining lesson 65 with simplifying fractions, okay? So if we understand, let's just put it this way. We know, ... Let's say we had 2 times 3 times, no, not 4. Let's times 2 again. It's supposed to be prime factorization, sir. We know that we're allowed to do this thing where you say the 3's would cancel and the 2's would cancel, and you'd be left with 6. But I want you to think back. What must have been the original fraction to get this? Well, it would have been something over 6, right? 2 times 3, 6. 2 times 3, 6. 36. We know that if we had 36 over 6, that's going to be 6, sure, but here's a way to prove it using the prime factorization of 36 and 6. So, all we're going to do is a problem similar to that, but it's not immediately easy to do. So let's do 156 over 26. So we're going to use the prime factorization to reduce that. It's not the only way to reduce it, but that's what lesson 67 is about, so we're going to do it. So we'll start 156. Do you guys know some factors that go in 156?
5, like
3? How do you know 3 does?
27?
Oh.
No. Because it's an odd.
26 has a 6. Does 3 go into that? Oh.
2.
What's the rule for divisibility by 3? Add the digits. What's 1 plus 5 plus 6? 12 is divisible by 3. Therefore, 156 is divisible by 3. But I'm not going to do that, even though Sophia's right. I'm going to do 2. It's even. Might as well. 2 and 78. Still even, so we'll do 2 and 39. Oh, 39. 39 sounds prime. But don't believe it, it's not.
It's divisible by 3.
All right, think back to our 3 rules. So we have 3 and 13. So here's what I got. 156 is going to be 2, 2. It's not time to go. I know you saw people in the hallway, but that's high school. 3 and 13. Now 26. Let's do 26.
Oh.
How does 26 break down? 2 and
6? Wait. No. 2 and
13. That's coincidental, right? So 2 and 13. And why did I write it like that? Because I want you to see it. 2, 13.
2, 13.
So what's the answer to that?
6.
6 over
30.
36. 26.
15.
everything canceled out. So it's not 0, it would be a 1. And 6 over 1 is the same thing as just 6. So the only new skill here from 65 is let's use it to reduce a fraction.